This is Geometry Lesson 12.6, the SSS Similarity Theorem. So that should sound familiar. We looked at congruence theorems. So we're now going to be looking at some similarity theorems. The big idea says if the ratio of the lengths of all three pairs of corresponding sides of two triangles are equal, then the triangles are similar. And the theorem itself says if the three sides of one triangle are proportional to three sides of a second triangle, then the triangles are similar. So we have kind of already studied this without actually getting specific about it. We know that's how to tell if things are similar. You match up all the corresponding sides, and if you get the same ratio, it means they are all proportional, and therefore they are similar. So we're kind of looking at going backwards and proving it. And we're not necessarily going to be writing formal proofs here, but we are going to prove that things are similar by showing that everything is in proportion. All right, so let's jump right in. Applying the SSS similarity theorem. So one way to tell whether two triangles are similar is to go ahead and order the sides. That's important. Order the sides by their lengths and then compare the ratios that are formed by their corresponding lengths. So what does that mean? So let's say we're given these two triangles here. Now this picture, it's pretty easy to match up which sides go with which, but it's not always true. And you'll see on the next example right below it that you're just given numbers and you're not given a picture. So how do you match up the correct sides? Well, it's pretty straightforward. You just put them in order. The smallest side goes with the smallest side. The biggest side goes with the biggest side. So specifically for this one, let's say you didn't have the picture and you didn't know how big 64/3 was. Just go ahead and divide it, not the fraction button, just divide it and get the decimal version, 21.3, and you can clearly see 21.3 is bigger than those two. So if I was going to put those in order, I'm going to have 8, I'm going to have 16, and I'm going to have 64/3. And then what I'm going to do is I'm going to order the other ones right underneath of it and form my corresponding ratios, and we'll see if they actually are the same. So the smallest number in this triangle is 3. The middle number is 6. And the biggest number is 8. And so what we're going to do is we're going to go ahead and simplify these. These would all need to be equal if these are going to be similar. 8/3 doesn't simplify. It doesn't give us a nice decimal version either here, because when you divide by 3, you get those repeated decimals. So it's 2.6 repeated. You could just check all of them and see if you get 2.6 repeated. But we're going to very often want to state the scale factor or the ratio of similitude, and I don't want it as 2.6 repeated. So we're going to leave it as a fraction. We're going to leave it as 8/3. 16/6, I can divide both of those by 2, and I get 8/3. Remember that you can also punch that in the calculator. So if I have 16/6, that simplifies to 8/3. And now that's what I'm going to do here. 64/3 divided by 8. Let's punch that in. 64/3. Now you could try and make it another fraction, but just go ahead and hit divided by. That's what we're doing here. Dividing by 8. And sure enough, same answer, 8/3. So the question's asking us to determine if they are similar. These are all equal to each other, equal ratios. So we're going to answer that question in a full sentence. All the ratios are equal. Therefore, they're similar by the side similarity theorem. So I am going to specify there that it's the similarity theorem, not just the SSS theorem, because we've talked about a different SSS theorem, the congruence theorem. If three sides of a triangle are the same size or congruent, then we know the triangles are congruent. And that's not what we're proving here, right? These are not the same size. These are not congruent, but they are similar. One is an enlargement of the other. One's a reduction of the other. It's the same triangle. It's just been enlarged or shrunk. And so they are similar. And so it's the SSS similarity theorem. All right, so real quick, let's try this one. I would say maybe pause your video, give it a shot, see how you do. So we're going to go ahead and line these up in order. So they were not given to us in order. Be careful. So 24, 40, and 56 are the sides of the first triangle in order. Smallest of this one is 42, then 70, and then 98. So I'm going to go ahead and simplify these. Some of you can do that quick in your head. If not, use the calculator. So that's 4 over 7. Now 40 over 70, we should see that one. Divide by 10, that's 4 over 7. And then 56 over 98 also is 4 over 7. So determine if the triangles are similar. So I'm going to say yes by the SSS similarity theorem. All right, example number 2. It says at the right we have two triangles. Some of the side lengths are given. So we're missing this one right here. If you look, I have every side length except that one. The angle measures are approximations to the nearest tenth of a degree. So these were rounded originally. That's why they say they're approximations. So if these are similar, what's the ratio of similitude? So as we look at this, you can kind of match things up here in the picture, but we want to make sure that we get the biggest side with the biggest side, and so on and so forth. So we can't just randomly grab any side and put it with something, although I do think this does match up in a way that you can see it. But here's the trick. Make sure that you look at the similarity statement and you match up the sides with the sides correctly. So FE, the first two letters, goes with GO. So FE, this 5, if you couldn't tell in the picture, goes with GO. And so that's the side that we don't have. So if we look at ED and OV, here's ED and here's OV, those sides do match up. Okay, so they're in a 3-to-1 ratio, 3-to-1. Now, you could also match up the other ones, 6-to-2. Right, 6 over 2 is going to simplify to 3 over 1. So if these are similar, the ratio of similitude or the scale factor, remember that's the same thing, is 3-to-1. Or if you're going the other direction, you flip it, it's 1-to-3. 2 over 6 would simplify to 1 over 3. All right, so there's our scale factor. So using that information, what length of GO, the missing one right here, let's call it X, would make this similar? So this one is going to have to match. All three sides have to be in proportion. So we need a number here that when you match it up with its corresponding side, which is 5, will give us this ratio of similitude. So let's just think about the numbers here. If I'm going from right to left, it's 2 times 3 to get 6. It's 1 times 3 to get this. If I'm going the other way, it's 6 divided by 3 to get 2. It's 3 divided by 3 to get 1. So since I have this number, I'm going this direction, it's going to be 5 divided by 3. If I'm going this direction, divided by 3, this way would be times 3. And I'm going to go ahead and just leave that length right there. If you plug that in, you're going to get a repeated decimal, 5 divided by 3. And we do need to know that that's 2/3. It's 1 and 2/3. 0.6 repeated is 2/3. We need to recognize that. But I wouldn't write my length here as 1 and 2/3. We kind of stay away from those mixed numbers. Just leave it as an improper fraction. 5 over 3 is just fine. All right, and then finally part C, let's estimate the measure of all the angles in GOV. They are going to match. We've talked about that any shapes that are similar, the angles do not change, even though the side lengths have gotten bigger or smaller. And so we're going to go back to our similarity statement and match things up. I already know F is 29.8. F matches G. It's in the first position right here. So I automatically know that G, and I'm not going to write equal to because remember, these were approximations. So I'm going to put the squiggle. This was rounded. G is approximately matching F, 29.8. I have D. D is in the last position. It's going to match V. So V is going to be the same number, so approximately 55.2. And then if I want to find my other one here, that would be O. That's going to match E, which I don't have, but I have 2 out of 3 measures of a triangle. So I'm going to do 180 minus those, 29.8 minus 55.2. All right, and it's approximately 95. You might want to write that down so you know what you did. And now I have all three triangles, or all three angles, I should say, of my little triangle. All right, as I go to the back now, we're going to look at some very specific common triangles that have certain side lengths that are all proportional. And so I'm going to go ahead and read this to you, but these are the numbers we're going to be looking for. There's special 3, 4, 5 triangles, 5, 12, 13s. We've talked about those special 30, 60, 90s, right? And those 45, 45, 90s. These are different common triples where the side lengths come out to nice whole numbers, or they're going to be factors of them, or not factors, multiples of them. So because of the SSS similarity theorem, if you multiply or divide the lengths of three sides of any triangle by the same number, the triangle with the new side lengths will be similar to the original. That just means if I take any, even if they're not these special numbers here, if I have the three side lengths, I multiply them all by the same number, that new triangle, that bigger triangle, is going to be similar. It's just an enlargement of the original. So here in math terms, they say A, B, and C are the lengths of the sides. I'm multiplying them all by the same thing. So K is a number that I'm multiplying all of them by. That's going to create the side lengths of a similar triangle. Now, this is especially true. What we're going to focus on here are these special common triples. So remember, if you want to test if something is a right triangle, you set up Pythagorean theorem. This would be my C. C is always the biggest number. So the 3 and the 4 can go in either spot. 5 must go in the C spot. If I want to test to see if this is a right triangle, both sides need to come out equal. 3 squared is 9, 4 squared is 16, 5 squared is 25, 9 plus 16 is 25. So this is a right triangle. So a 3, 4, 5 triangle is a very common right triangle. And so we're going to see other triangles that are similar to it that are just enlargements of it. So if this triangle was enlarged by, say, 10 times, we're going to create a new triangle with sides of 40 and 30 and 50. And these are going to be proportional, so they are similar. And so we'll start to recognize these. Now this one's real obvious because you see the 3, the 4, and the 5. But what if you see one, and let's say it's 6 and it's 8, and you're missing this side. Now you could always just do a squared plus b squared equals c squared. But what we're going to study here is we're going to look at these common triangles that we can recognize that we know are always going to be a right triangle that helps us find a missing side without having to run through the formula. So if I notice that this is the 3 being times by 2, and this is the 4 being times by 2, I automatically know that this other side is my 5 side, and I automatically know that this is 10. Okay, so we're going to start recognizing these. 5, 12, 13 is a very common one as well. Those are the two most common ones, and we'll see these sometimes, but really we're looking for 3, 4, 5s and 5, 12, 13s. 5 squared plus 12 squared should equal 13 squared. That's 25, that's 144. 13 is 169. Those add together, and they do end up being equal. This is another right triangle. So if I see multiples of these numbers, or they show up in a fraction, that's what we're going to look at here, I can just jump right in and solve for that missing side based on the Pythagorean triple. I don't actually have to run the Pythagorean theorem. So as we look down at example number 3, you can see right here, here's the 5, here's the 13. And so for now, you'll probably need to reference back to these, but you'll start to memorize 3, 4, 5, and 5, 12, 13. Maybe not these because we don't use them as much, but you definitely want to recognize those first two. And so this is a 5, 12, 13 triangle. And of course, you could run a squared plus b squared equals c squared, and you would quickly find out what this answer is here. But because we can see this is just times 10, it's a 5, 12, 13 times 10, I automatically know this one right here is 120. Again, if you ran it out, I'm not going to run it all the way through, but you would do 50 squared plus x squared equals 130 squared. And if you ran that all the way out, you would end up with x equals 120. You would. But we now no longer have to do that if we recognize one of these special triples. So that's what we're looking at here. Okay, so the next question right there, a right triangle has a hypotenuse. So remember that means across from the 90 of 170. One of the legs is 150. Find the other leg. Of course, you could do x squared plus 150 squared equals 170 squared. It will get you the answer. But if we start to recognize that this is one of these special triangles, which in this case we can see here's the 15 and the 17, not one we tend to memorize as much, but since you have it here in your notes, you can reference it. I've got the 15 and the 17. And so this must be the 8 side. All of these 8, 15, 17 were just times by 10 to get these numbers. So I automatically know that x here is 8 times 10, 80. Okay, example number 4. Use a Pythagorean triple to find the missing side length. So we've got fractions, but we're just looking at the numerators here. Okay, they're in proportion. I have a 3 and a 5, so this is a 3, 4, 5 right triangle. And so the 4 is going to go here and it'll be over 7, just like those. So I know that this side length is 4/7. And again, if you ran it all the way out, 3/7 squared plus 4/7 squared. And if you were putting this in your calculator, you would want to make sure you're not just squaring the numerator, you're squaring the whole fraction. It will equal 5/7 squared, and if you ran that through, it will come true. All right, so we no longer have to do that if we recognize the special Pythagorean triple. All right, last one. You have a right triangle. Hypotenuse, meaning across from your 90, is 15/8. One of the legs is 9/8. Find the other one using a Pythagorean triple. Now I'm looking at these numbers here on top, 9 and 15, and I don't see a triangle that has a 9 and a 15. So how am I going to do this? What I want you to start to recognize is these are multiples of one of these common ones. And in this case, it's actually a 3, 4, 5. All right, this is 5 times 3, and this is 3 times 3. So this is a 3, and this is a 5. So we want to start to recognize that, okay, the 9 and the 15 are not numbers in a triple. But just like we saw these, now we actually saw the physical numbers, 1, 7, 1, 5. But these are multiples, they're times 10. So these are the same thing. These are multiples, they're times 3. Okay, so this is going to be my 4 side. And so this was 3 times 3. This was 5 times 3. This is going to be 4 times 3. Right, this was times 3 times 3. So 4 times 3. That would give me a 12/8 for my missing side. So again, to prove that this would work, 9/8 squared plus 12/8 squared should equal 15/8 squared. If you were doing this on an assessment and you wanted to check your answer to see if you had it right, you could. You're just going to plug this in here. So using your fraction function, you're going to do 9/8 squared plus 12/8 squared. That comes out to 225/64. I don't expect you to do this every time, but it might be nice to check your work on a test and know if you've got it right. And then, so that should equal the other side if this is correct. So I'm going to do 15/8 squared. And sure enough, I get 225/64, and I know my answer is correct.